Okay, thank you very much, Martin, and I'd like to thank the organizers for this opportunity to come back to Lumini and to CERN. I want to give a talk about the relationship between some very naive and elementary problems about billiards and polygons and some elementary number theory. And I'm a completely amateur at number theory, so I may get some helpful comments after the talk. Please feel free to pass those along. So let me also mention that the work I'm going to describe builds on the work of a lot of people. So there's a development that's kind of independent of the modern theory of billiards and polygons due to Leutbecker, Cohen, Wolfhard, Borho, and Rosenberger. And then there's a more modern strain consciously related to Teichmüller curves and polygon, work of Veach, Maser, Müller, Viehweg, Davis and Liliev, and Smiley and Ulsegai. And then three other authors who you may not know, Everett, Lin, and Maget, did some work directly related to a question I'm going to discuss. So, there's lots of different kinds of questions one can address when studying billiards, and I'm going to focus not on the behavior of random trajectories or typical trajectories, but rather the behavior of periodic billiard trajectories. And the kind of question that we want to ask can be seen already in the case of billiards in a regular pentagon. So I'll take this as my motivating and prime example. I'll return to it over and over again. So here's an example of a periodic billiard path in a regular pentagon. It's interesting to try to find such paths that close, and it's known that there's a dense set of slopes such that the corresponding trajectory is periodic. Also, once you find a slope such that one trajectory is periodic, it turns out all trajectories with that slope are also periodic. So there's a dichotomy in the slopes. Some are, quote, periodic slopes, and some are not. So we can ask which slopes are periodic, and how do the periodic trajectories behave? So let's turn to a simpler instance of this problem that's familiar to many or most people, to give an idea of the elements of the solution. So suppose we considered instead periodic trajectories for billiards in a traditional pool table. Now, it turns out a rectangular pool table has essentially the same billiards as a square. So I'll make my billiard table square, and then there's lots of periodic trajectories. And which slopes are periodic? That's easy. The set of periodic slopes is just the set of rational numbers, p over q. These are the periodic slopes for a square. And there's lots and lots of different periodic trajectories, and they have complicated combinatorics in terms of the number of sides they hit and so on. But there's a way to analyze the dynamics of billiards in a square, which is very natural. Namely, you identify opposite sides of the square, and then the result is a Riemann surface. So if I call this, I'm going to call this a polygon P, and the notion of a straight line is recorded by the differential dz. When I apply dz to a vector, it gives me a complex number which measures its slope, and the straight lines are just the paths where that slope is constant. And so this pair, consisting of the polygon and dz is invariant under translation. This should only have one dash. And so when you glue this up, you get a standard elliptic curve, which is the quotient of the complex plane by the Gaussian integers. And on this elliptic curve, there's a one form, which is just the form dz coming from the square. Or coming from the complex plane. And then the nice thing about passing to this model is that the periodic billiard trajectories go over to geodesics with respect to the flat metric on this torus, closed geodesics. Let's see if I can get this to close. There we go. And of course, there's lots of closed geodesics. And again, the slopes of closed geodesics correspond to rational numbers. But the really interesting thing is that there's a renormalization group in play. So what's the renormalization group here? It's just SL2Z. So the idea is, for a moment, you forget about the complex structure on the torus, and you think of C as being R2. And then a matrix in SL2Z is exactly a real linear map that preserves the Gaussian integers as a lattice. We then can think of the Gaussian integers as just being Z2, sitting inside of R2. And so it descends to give an automorphism of the torus, not a complex linear automorphism, just a real linear automorphism. But this automorphism preserves the notion of a straight line. So this renormalization group sends straight lines to straight lines. And so we can take a billiard trajectory we don't understand, and we can try to map it to a very simple one, which we do understand. And in fact, the action of this renormalization group is transitive on the space of periodic slopes. And what we learn from this is that there's only one type of closed geodesic on the torus. Every closed loop is equivalent, up to this simple change of coordinates, to whatever your favorite loop is on the torus. Say the one with slope infinity, or with one of the generators of, the obvious generators of pi1. Okay, so, and then this comes back to haunt the square. There's a little work is required to go back and forth between the torus and the square, but what we find is that this gives an easy proof, not that this is difficult, that the periodic slopes in the square are also rational numbers, but it brings to the fore this group. And so, so this is a prototype for what we want to consider for more general polygons, and as I said, I'll focus on the Pentagon and then also on regular n-gons in general. And here's a reminder of how the group SL2Z acts on the upper half plane. This is its standard fundamental domain. It's acting by Mobius transformations. All of these lines are equivalent under the action of SL2Z. And perhaps most importantly, if you draw a horizontal line here, you can think of that as a circle tangent to the point at infinity. And the images of this circle are drawn here below. They're orbit under the action of SL2Z. And there's one circle for each rational number. Each circle rests on a rational number. And that's equivalent to saying that this fundamental domain has only one cusp, and that its orbit under the action of SL2Z consists of the rational numbers. And maybe I'll pause for a second just to think about how lucky we are that we understand SL2Z so well. So if I look at the group SL2Z, it consists of integer matrices that satisfy a simple equation. And if you ask me what numbers can occur as matrix entries, I know the answer, every integer. So A can be an integer. What numbers can occur as columns in a 2x2 matrix of this type? Well, because of this relation, A and C have to be relatively prime. And that's a necessary and sufficient condition. So we know exactly what the columns are, and we also know what the matrices are. They're just the integral points on this particular quadric. And that reflects the fact that SL2Z is what's called an arithmetic group. An arithmetic group is one where you understand the group extrinsically. You can give an extrinsic description and quickly test whether or not a particular matrix belongs in the group using things like congruence and whether or not it's an integer. Okay, so now let's come back to the Pentagon and see if we can carry out a similar program. So here's an experiment that I first did maybe 20 years ago, a little more than that. So what you can do is you can try taking a periodic slope and seeing what the trajectory, what the closed trajectories look like. So here my slope is parallel to this edge, and I get a little star as the periodic trajectory. So the slope was very simple to describe, and it gave a trajectory with 5 segments, so its combinatorial length was 5. Now, if I just multiply this slope by 4, I get 469. It hits the sides of the Pentagon 469 times. There's 469 segments in this picture. Even though this number is pretty easy to describe, it's 4 times the previous number. And if I take 20 times the previous number, I see 2,338. Can you see they're a little bit too thick to count? And if I take a random number like 6,765 times s, then there's about 10 to the 25 segments in the trajectory. And by the way, you might wonder, how did I ever calculate how many segments there were? That's a kind of interesting problem in its own right. So what we see is that in contrast to the square, where if the slope is like p over q, then the number of segments in the trajectory is like the maximum of p and q, up to a constant. But here, the complexity of a closed trajectory grows very rapidly with respect to the complexity of the number describing the slope. And in fact, when you first start looking at this, you think, oh, well, most possible slopes cannot be realized because you run your computer for a day and a half and the trajectory never closes. But in fact, there's a theorem which says the periodic slopes coincide with everything they can be. That is, there's an associated real field here, which is q adjoin the square root of 5. You take that initial slope that I mentioned, and any multiple of that slope by an element of this field is periodic. So we're in a situation that has some similarity to SL2Z. We can say exactly what the periodic slopes are. But what's hard is to say how long they are. So what's known is that the log of the length, which is the number of digits in those numbers I was writing down, the number of times it hits the sides, is bounded by, so to speak, the log of the slope squared. So that this is actually the height of the slope. It's sort of the number of digits you need to write down what the slope is. So if you have a slope that you can write down in 5 digits, then its length might be 10 to the 25. If it's 10 digits, its length might be 10 to the 100. So this exponent turns out to be sharp. So that's the situation for the slopes in a pentagon, and we see this very sharp transition to added complexity. Now, I'd like to go back to the picture for the square and try to mimic some of the ideas. So for the square, we built a Riemann surface, which was a Riemann surface of genus 1. What do we do if we want to unfold the trajectories in a pentagon? What we do is we take 2 copies of the pentagon, and then when a trajectory hits an edge, instead of having it bounce, we have it just move into the adjacent copy of the pentagon. And then when it hits this edge, we could put another pentagon underneath, but that would be the same as the one on top. So instead, when this trajectory hits this edge, we just have it restart up here. And so to analyze bouncing trajectories in the pentagon, it suffices to analyze straight line trajectories in the Riemann surface we get from 2 pentagons by gluing opposite sides. And this object here has 8 sides, so when you glue opposite sides, you get a Riemann surface of genus 2. And so that's the natural province for the study of billiards in a pentagon by relating them to straight line geodesics on a closed surface. So that's the first step in our discussion, is to go to a Riemann surface, and then we start to get into number theory. Number theory was in the title of the talk, so I'm allowed to do this. So in general, when we study billiards in a regular n-gon, there's the nth root of unity obviously plays an important role. Even to draw the picture of the regular n-gon, one uses the nth root of unity in the complex plane. And then there's a cosine. 2 cosine 2 pi over n is the same as the real number obtained by taking the trace of zeta n, i.e. adding it to its complex conjugate to get twice its real part. This generates a real field. And so we have a chain of fields when we're studying the regular n-gon. We start with the rational numbers. We have Q adjoined the nth root of unity, and then it has a totally real subfield of index 2, which is generated by this number a to n. And then there's corresponding rings of integers in these fields, and it's as simple as possible. The ring of integers in this cyclotomic field is generated by the nth root of unity, and the ring of integers in the real field is generated by this epsilon n. Okay, so now what I want to tell you about is what's the renormalization group? What takes over for SL2Z when we study the Pentagon? And it turns out that the group in general to study the n-gon is very simple. It's a matrix group again. It's ax on the upper half plane. And its entries are algebraic integers this time instead of ordinary integers. And it's generated just by these two matrices. So this is a 1 here. So upper triangular and lower triangular matrices. These are supposed to be parabolic. And it sits inside this big group of matrices with integer entries in this field. But once this field is quadratic or more, this is a dense subgroup of SL2R. But this is a discrete subgroup of SL2R, the group generated by these two parabolics. And by the way, there should be, somewhere in this group, there should be a renormalization that corresponds to just rotating the n-gon, and that's this product, u times t. So this group is arithmetic, once again, but that's not the group we need. The group we need is this one, which is generally which is always of infinite index in this one, once we get beyond the case where k is the rational numbers. So for almost all n, this is what's called a thin subgroup of SL2OK. But nevertheless, the geometric picture is very similar. You see for the Pentagon, there's a fundamental domain which looks a lot like the fundamental domain for SL2Z. This would be translation by 1 for SL2Z. Here it's translation by the golden mean. Here's the parabolic element u. So u fixes the origin, t fixes infinity. Here's the promised rotation. The composition of u with t fixes this point in the upper half plane, rotates with order n. These are all fundamental domains. So as you can see in this picture, once again, the group has only one cusp. And what that's telling us is that from some interesting point of view, which has to do with the surface of genus 2, although there's lots of billiard trajectories in the Pentagon, there's really only one. That's what the fact that somehow the periodic trajectories will correspond to the cusps of this group, by which I mean to the points down here, which are the image of the point at infinity under the action of the group.
Sure.
Yes?
So you said that delta 5 is thin.
Yes?
It's a thin group. So the quotient has infinite or real.
No. So it's thin in the arithmetic group SL2OK. SL2OK is, so let's think about the,
Okay,
yes? Yeah. So it's thin in a group which naturally wants to live in the product of two copies of SL2R. Yeah, good point. So if I'm going to add in as I go some references to topics I won't have time to develop in this talk, but I hope the pictures allow you to also stay down to earth. This is just a new version of SL2Z, and it happens to use the golden mean in its definition. Okay, so what can we conclude from this new discussion for the Pentagon? Well, if we understand this group well enough, then we should be able to, by analogy, figure out what the periodic slopes are. And so the theorem is, and this works not only for the Pentagon, but also for the octagon, the decagon, and the regular 12gon, the cusps of this group, which correspond to the periodic slopes in the regular n-gon, they're as big as they can be. So they coincide with the projective line over this real field, which I just introduced. So this generalizes the statement that I just made for the Pentagon. And indeed, these numbers, 5, 8, 10, and 12, those are exactly the numbers where this field K is quadratic over Q. So when the field K is rational, we're in a very easy to understand situation, that's SL2Z. When it's a little bit beyond rational, it's quadratic, there's still a lot we can say. So we don't know very much about the columns of this group, but we do know something about its cusps. Namely, its cusps are everything. And so corresponding to the fairy packing, which I showed previously, there's a bunch of circles that are invariant under the action of delta 5. And they notice that there's 5 of these circles around this vertex here. If we think of this region up here as a circle, 1, 2, 3, 4, 5. And there's something similar to that for every value of n. But here, we know where the circles sit. They sit on top of the elements of the field Q adjoin the golden mean. And now, there was the question of how long is the trajectory? And in the case of SL2Z, the natural ball sitting on top of P over Q has height roughly 1 over Q squared. Here, these balls get small extremely fast, but not unbelievably fast. And the size of the ball is what tells you how long the trajectory is going to be. And that has to do with predicting the columns in this matrix. And we don't know what the columns are, but we can extract a bound for them in the case of quadratic fields. And here's another way to say what we know about this group, if you like continued fractions, and this is another version of renormalization. So if you start with an element in the field generated by the golden mean, or golden ratio, as I've learned it's called in other cultures, you can take this element and try to write it as an integral multiple of the golden mean, and then there'll be some leftover remainder, and you take its reciprocal and try to write that as a multiple of the golden mean. You keep going, and the remarkable fact is that this so-called golden fraction eventually terminates for every element of the field generated by the golden ratio. So that's in fact equivalent to the statement that every element of this field gives you a periodic slope for billiards in the Pentagon. And if you can compute this continued fraction, you can compute a lot of information about that periodic slope. And so for example, this height bound I was mentioning tells you an upper bound on how long it's going to take you to build this continued fraction. So it turns out you only have to do this roughly n steps, where n is bounded by the height of the number x is equal to s of the number s that you started with. So there's an effective algorithm to compute this continued fraction. You know how long you have to wait. Now, just for perspective, let's take a glimpse at what happens for cubic fields. So here's an unsolved problem. Let's look at what happens for the regular 7-gon. So we could ask the same question, which slopes are periodic? So there's one, and here's another. Now, I believe the slope 2 times the first is not periodic, but that's quite hard to prove. And in fact, the following is an unsolved problem. Of course, if a slope is periodic, you can eventually discover it by simulating the billiard flow. But what if it's not periodic? Well, if we knew how long we have to wait for it to become periodic, say in terms of some data describing the original slope, then we would have an algorithm for test for the periodic slopes. But the periodic slopes turns out to be a proper subset of the field in this case, and there is no known algorithm to test if an element of that field is a cusp. Is there any algorithm at all to test? So this is I think, quite remarkable that such an elementary question, you change 5 to 7, and we're lost. But cubic fields are very different from quadratic fields. So as quadratic is 1 plus 1, and the first one can beat the second one. But cubic fields are 1 plus 2, and the first one cannot necessarily beat the 2. I'll try to make that more precise later. Okay, so now I want to take a glimpse at some more questions about dynamics in the Pentagon. So we can also ask, how do these periodic trajectories fill out the regular Pentagon? And then there's a beautiful fact known due to Veitch. This is called the Veitch dichotomy. It says if you choose a billiard direction that's not periodic, then it fills out the Pentagon evenly. Now here I drew a periodic trajectory that comes back to where it started, but it's very long. And as you can see, it appears to be filling out the Pentagon pretty evenly. So you might ask, what is the distribution of a long but periodic trajectory? And don't guess yet, because there's this beautiful example that was found by Davis and Liliev of longer and longer trajectories that leave a hole in the middle of the Pentagon. So although a typical trajectory is uniformly distributed, long periodic trajectories are not uniformly distributed. They can accumulate on some other measure on the Pentagon. And so Davis and Liliev observed this phenomenon, and they ask, what kind of measures can you get from long periodic trajectories? For example, is there a Cantor set of measures that arise? And they found a tree-like structure to this space of periodic trajectories. So it was natural to think of the ends of this tree. But it turns out that the limit measures form a countable set. And this countable set is homeomorphic to the ordinal omega to the omega plus 1. And what this means is that there's an accumulation point of the measures, then there's an accumulation point of accumulation points, then there's an accumulation point of accumulation points of accumulation points, and this goes on countably many times, and then there's finally one more point. And that last point is uniform measure on the Pentagon. So you eventually get there.
This theorem is just about the Pentagon.
This theorem is more general. It works for arbitrary billiard, works for Teichmuller curves. Okay? But I'm illustrating things with the Pentagon today. So this describes, in fact, in the course of proving this theorem, one gets a description of what's called scarring in the business. Scarring is the failure of these trajectories to be uniformly distributed. And it also gives a description of the closure of the ergodic measures for the billiard flow.
Can you state the theorem again?
Yes. Yes. So also,
You fix the slope?
right. So I fix a slope, say slope 0. And then I take periodic trajectories with slope tending to 0. Now, I don't want to just take periodic trajectories with slope 0 because there's only a bunch of parallel ones. So I let the slope converge to 0, and I look at what measures I get in the limit. And that's what this M sub s is. And then that particular space is a copy of omega to the omega plus 1. And I don't want to dwell on this theorem. It's just to give a little more of a panorama. But I do want to show you that this is extremely explicit. One can compute what the space of measures is for the Pentagon with slopes tending to 0, as Sayers just clarified. Thanks for that question. And here's uniform measure. And you can, if you look closely, you can see a first accumulation point. And then, well, somewhere down in here, there's a lot of structure in this picture. But let me just mention two things about this picture. The first is, remarkably, the space of limit measures forms a semi-group. There's a natural group law on this omega to the omega plus 1. And the other thing I want to mention is that it's telling us a little bit of information about the matrix entries in delta 5. So if we take this matrix here, A, B, C, D, to be in delta 5, remember, this is a group for which we've given generators. But we don't have an algorithm, or at least a simple way, to test or describe the matrices that lie in this group. The best you can do is generate them by taking products of the generators and their inverses. So we don't know, for example, what numbers can arise as this top matrix entry here. But what this picture is showing you is the collection of real numbers of the form A prime over A, where A prime is the Galois conjugate of A. Remember, we're in a quadratic field. So if A, for example, could be any element of this field or any integer in this field, then this set of real numbers would be dense. But in fact, A prime is always less than A, and the collection of these ratios is exactly the same as determining this set of limit measures. Okay, so I'm going to skip most of the methods for the moment, just to get some statements in play, and I'm trying to show just a glimpse of contact with number theory, which will become more precise as we go. I just want to say there's something in number theory called a modular symbol, and that's what's used that's the underlying process behind this discussion of the limit measures. Okay, so now I want to come to some more recent developments. And I'm going to stick with the study of cusps, which we've seen is coextensive with the discussion of periodic trajectories. And I'm going to ask some questions which turn out to have, so to speak, periodic answers. That is, the answers to these questions can be determined by taking your slope and reducing it modulo a prime, for example, reducing it mod 2. And maybe before I do that, let me just say what reduction mod 2 means. So the first thing is I like to specify a slope, say for the regular pentagon. It's nice to normalize the pentagon so this vector is 1 and this vector is the primitive fifth root of unity. And then it turns out that the periodic slopes are specified by elements in my field L, which was Q adjoin zeta 5. Or equivalently, they can be, I just want to get the direction, so you could specify them by an algebraic integer in this field. You see, if you're going to have a periodic trajectory, if you unfold this pentagon, there will be a path which leads from its beginning point to its end point, and that path will be built out of copies of the edges of the pentagon, so it will lie, the distance, the vector between its endpoints will be an element of this ring. So the periodic slopes coincide with the directions in this ring, and so that's how I'm going to specify them. So you can think of this ring as being a module over OK. Remember, OK was the real subfield generated by, say, the golden ratio. And so you can think of this ring as being OK plus OK times something else, say OK times zeta 5. And so the space of directions, of periodic directions, is so to speak, the projective line corresponding to this rank 2 module over the ring OK. So let me just bring that down to earth. It turns out that the periodic trajectories correspond, after a choice of basis, to P1 of OK. And that's roughly like saying, oh, the slope just has to be an algebraic integer in this in Q adjoin the fifth root of unity. It's slightly more than that, but I don't want to belabor that at the moment. The most important thing is that when you have a direction that's specified as a ratio of two integers in this ring, then you can take these two integers and reduce them both modulo a prime or modulo some other number. And I'll be particularly interested in taking this ratio and reducing it mod 2. By that I mean we take the quotient of the ring OK by the ideal generated by 2. Now if OK were the integer, Z mod 2 would be the field with two elements. But in general, this is not even a field, this quotient ring. On the other hand, naively, it has a lot to do. It's pretty easy to compute with. And there's a reason why 2 is going to be important. I'll also do reduction modulo some other things. But this is the main point, is that there's a process that takes a slope and gives you a point on a finite projective line. In fact, let me make one more statement. So if you take the case of the golden mean, the golden ratio, if you take z adjoin gamma is what? This is z adjoin x modulo x squared minus x plus 1. That's the minimal polynomial for the golden mean. So this is O. If you take O mod 2O, what you get is, what you do is you replace z by the field with 2 elements, and then you mod out by the same polynomial. And this polynomial turns out to be irreducible mod 2. And so this quotient is just the field with 4 elements. And therefore, the projective line is just F4 union of point at infinity. In other words, the projective line has 5 points when you're playing this mod 2 game with the Pentagon. And that's very pleasant, because the Pentagon has 5 sides and 5 vertices, and it all fits together very nicely. OK, so now let's try to state some results. So let me just show you another experiment. So when we study particular billiard paths, we might want to do the following. We pick a periodic slope, and then we change where we start our trajectory. I didn't say much about where we should start our trajectory. I learned from Diana Davis and Sam Liliev that I should start my trajectory at an edge midpoint. Why should I start at an edge midpoint? Well, there's 2 reasons. One is these trajectories come in parallel families, and every parallel family has a representative that starts at a midpoint. But the other reason is when you build the Riemann surface of genus 2 associated to the Pentagon, it has 6 special points on it. These are called its Weierstrass points. And 5 of those correspond to the edge midpoints, and the last one corresponds to the vertex. All the vertices become identified in the quotient. So secretly, these are the Weierstrass points of a hyperelliptic surface of genus 2. But if you like, they're just the edge midpoints. OK, so here's the interesting phenomena. I pick a slope. So I picked this slope of 0 degrees here. So I started at this edge point, at midpoint. I went horizontally, boink, 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 boink. I came back to where I started. Good, that's periodic. Similarly here, I went horizontally. Now, here at the bottom, I went horizontally, and I ran along the edge until I hit a vertex. And I decided that wasn't very interesting, so I went the other direction, and I hit another vertex. So this is a very different kind of trajectory. I call that a vertex connection. And then we go to the next edge midpoint. Oh, and we see the star again. And then over here, we see the inscribed Pentagon again. So 2 things are happening as we let the starting point move around the 5 sides of the Pentagon. First, there's one special trajectory which begins and ends at a vertex. And then what we see to one side of that is the same as what we see to the other side. That turns out to be general. So here's a different slope. And as you can see, if I start at M1, then I get a trajectory that begins and ends at a vertex. Here's another slope. I get a trajectory that begins at one vertex and ends at another, passing through this midpoint. And in both cases, what I see on one side is the same as what I see on the other side. And what I see at the 2 ends of this sequence of 5 is the same. Now, this middle case is a little more interesting because this trajectory has full rotational symmetry, as does this one. But here, you only see one reflection symmetry to the trajectory. It's less symmetric than these other ones. And you indeed see a trajectory here which is identical to this one, but you have to rotate the Pentagon to see the difference here. OK, so we now have a new question we can ask, which is, given a slope, how do I figure out which of these disparate behaviors occurs for the different midpoints? In particular, how do I find the special midpoint where I get a vertex connection rather than a genuine closed trajectory? And by the way, this phenomenon becomes even more striking if you go to, say, 11 sides. So here, these are all trajectories with the same slope. I'm just changing the starting point, but you see quite a diversity of pictures. And then you see this guy, which is rather impoverished. And that's the special trajectory that has a vertex connection. So I'd like to know where the vertex connection occurs. And the theorem is that the vertex connection is a congruence invariant. So what this means, let me state the theorem, is that this will apply when n is odd, so n is 5 or 11. We look at a periodic direction specified by an element of our complex field L, and the theorem is that the trajectory t at slope s, starting at the kth midpoint, I call the bottom midpoint m0 and then go around the pentagon or around the n-gon, that this is a vertex connection if and only if, when I reduce the slope mod 2, I get the kth power of the nth root of unity reduced mod 2 on this finite projective line. So indeed, in the case of the pentagon, this finite projective line, as I just sketched, it only has 5 points on it. And those 5 points know about the 5 midpoints of the pentagon. And so you can find information about the trajectories by looking at the reduction of the slope mod 2. And when you have a property of a cusp, of a periodic direction that only depends on its image in this finite projective line, I call that a congruence invariant, because it only depends on the value of S mod 2. There's another kind of congruence invariant I want to mention. So as we saw in the preceding slide, there's a couple of different kinds of symmetries that trajectories can have in the pentagon. So here's a trajectory that has full dihedral symmetry, but here it's not nearly so symmetric. There's a special axis here. It's symmetric under reflection through the vertical axis, but it's certainly not invariant under rotation. So this I call reflection symmetry, this I call dihedral symmetry. This is as big as possible, this is as small as possible. And here's a similar example. This is a dihedral trajectory in the 7-gon. This is a reflection symmetry in the 7-gon. How do we distinguish when one of these occurs? And the answer is, well, the answer is a bit of a pain, except for the case 5, or 7, or 11, or other prime numbers. So this could be formulated more generally, but I think it's pretty tricky. Let me just say what happens when n is prime, though, because it's very succinct how you distinguish between these two cases. First, the prime p ramifies in the field q adjoin zeta p. It factors as this prime raised to the p minus first power. So this number is a prime factor of p. P is no longer prime when you add in the pth root of unity, but there's a naturally associated prime. And when you have a prime, you can take the valuation of a point in the field at that prime. That just measures how many times it's divisible by that prime. And the theorem is that the trajectories have dihedral symmetry if and only if the valuation of s at pi is equal to 0 mod 2. By the way, this can also be formulated in terms of some finite projective line. And when you do that, you can argue that most of the time, you see dihedral symmetry. There's p plus 1 points that could arise on this projective line, and only one of them gives reflection symmetry. So as p gets larger, it gets harder and harder to find these purely reflective symmetry examples. Okay, now, remember the renormalization group? Let's go back to the case where n is even. I stuck with n odd previously. When you take those matrices I wrote down and you look at the group they generate for even n, it has a different looking fundamental domain. Even though the description of the group was very simple and uniform in n, when n is even, the fundamental domain looks like this. And as you can see, there are two cusps. There's a cusp at 0 and there's a cusp at infinity, and they're not in the same orbit of the group. And what that indicates is that when you have billiards in a polygon with an even number of sides, there's two types of behavior that can arise. And the main new feature when you have an even number of sides is that the polygon has this natural center, and a trajectory that starts at a midpoint can pass through the center of the polygon rather than through a vertex. So we now have two special types of trajectories, One I'll call central connection, and the other one I'll continue to call a vertex connection. So here's some examples in the regular decagon where you see these central connections. And it turns out that in the decagon, no matter what slope you pick, provided it's periodic, you either see a central connection or a vertex connection, but you don't see both. And in the octagon, the same phenomena arises. Here's a vertex connection, and here's a central connection. And in this case, every slope either has both a central and vertex connection or none. This is the case where n is 0 mod 4. So I won't state the theorem in detail, but roughly speaking, for certain values of n that are even, the location of these central and vertex connections can be computed by reducing things mod 2. They're congruence invariants. But this only works when n is equal to 2 mod 4, or, like in the case of the octagon, when it's a power of 2. Now you'll remember at the beginning, I mentioned that there's some special values of n that I like a lot and that are studied a lot: 5, 8, 10, and 12. And the reason is that in those cases, we know what all the periodic slopes are. And so I've done everything but 12. What happens for 12? Well, this was a truly unexpected discovery when I was doing this investigation. And let me explain what happens. So we can examine slopes when n is 12. For any particular slope, we have a distinguished trajectory. But what we don't know is whether it's central or vertex. So we can find a trajectory, an edge midpoint, such that we know that the trajectory starting at that edge point is either a central connection or a vertex connection, but we don't know which. That doesn't appear to be a congruence invariant. Now, if it were a congruence invariant, it would be periodic. So I start with a very simple collection of slopes, 1 plus 2k times the 12th root of unity. Let me call that sk. And for each one, I write down a number, ak, which is, say, +1 if it's central, and -1 if it's a vertex connection. And this sequence would be periodic if this were a congruence invariant. And then I form W of t, which is the sum from 1 to t of these numbers ak. So this is like a path that's being generated by this data that I had hoped would be periodic. And this is what the path looks like. So in fact, it looks exactly like a random walk on the real line. And I know nothing about this path. I mean, well, OK, one thing I know is it's not periodic of period less than 5,000, because I simulated it that long. But many, many more statements appear to be true. For example, certainly the location of the walk divided by t should tend to 0. It should be like a mean 0 random walk. Maybe it satisfies a central limit theorem, et cetera, et cetera, et cetera. But in fact, at the moment, I don't even know a proof that this path is periodic. So this is some sort of transition.
Kurt,
Yeah, yes.
It's periodic? Did you mean to say that? Not periodic.
I don't know if it's periodic or not, yes.
How, if it's periodic of period?
10 million, yeah, yeah. I'm sure it's not. I mean, I will make a little bet with you. OK, so very close to things that are congruence invariants, we find somewhat remarkably apparently random behavior in this discussion. And so I tried for some time to prove that this is not a congruence invariant. And here, let me just say a little bit about my perspective on that question. So the group we were talking about, delta n, is a thin subgroup of this arithmetic group SL2OK. Let's say k is q adjoining the 12th roots of unity. So n is 12. So this is of infinite index. That's a reflection of the fact that it's a thin group. But remarkably, if we take the completion of OK, that is the inverse limit of OK modulo its ideals, and we take the closure of delta n in this profinite group, then this index is finite. And what one can show is that if this index is less than 5,000, that reflects the 10,000 test I did, then the location of the central trajectory is not a congruence invariant. And moreover, I'm pretty sure that n is 12, 24. So if somebody could just help me complete that proof, that would be nice. I believe that there's methods from the Galois theory of points on elliptic curves that would allow one to evaluate this value of n. Okay, so I think I either have 10 minutes left or -5. I'm going to pretend it's 10. Thank you. Oh, great. Okay. So let me end. I want to finish with a topic that is more analytical, but also relevant to all these billiard things. So hidden in the background of this theory is a discussion of curves on Hilbert modular varieties. And I don't want to belabor the technical background behind this. I want to get to some sort of concrete discussions. But here's the theorem I want to share with you. So associated to our renormalization group gamma is a curve mapped into moduli space. This is what's called a Teichmüller curve. It's an algebraic curve in moduli space. And it always has a cusp. That's a theorem of Veitch. And what that means is that in all these billiard discussions, there's at least one periodic direction. So for some reason, these curves, which are totally geodesic, they're as taut as possible in Teichmüller space, in moduli space, they always have to have cusps. They can't be compact. But it's known that these curves always factor through maps to what's called a Hilbert modular variety. And so what I proved is that this theorem about the cusps of these Teichmüller curves is a consequence of a theorem which doesn't mention moduli space. The theorem is that the cusps of every geodesic curve on this Hilbert modular surface coincide with P1 of k. There's as many cusps as possible, and they satisfy these quadratic height bounds that I mentioned.
And Shimura curves are in null sets.
Sorry?
Shimura curves are in null sets.
Well, Shimura curves are in this quotes. Yeah. So those who know that this is false. Just omit those cases where it's obviously false. Okay, and then the results on billiards follow from this theorem that doesn't make any reference to Teichmüller theory. And by the way, there's other billiard tables that I haven't mentioned, and it applies to all the optimal billiard tables that we know. The regular n-gons are examples, but there's other examples like this. And it also applies to all the ones we're going to ever discover, because it's known that when you have an infinite series of these optimal billiard tables, that they have to be defined over a quadratic field. Now you might say, wait a second, the regular n-gons are not defined over a quadratic field, only for a couple cases. But that's what I call a vertical family of Teichmüller curves. The genus of the corresponding surfaces you build goes to infinity. But if the shape of the polygon, the number of sides, stays constant, then the only thing you can do is vary the side lengths in some real quadratic field. And then this theorem applies. We know the periodic slopes, et cetera, et cetera. Okay, so there's a way to factor this map, this Teichmüller curve, through a map to a Hilbert modular surface. And in the case of the Pentagon, that map is related to the fact that you can take the ideal pentagon in the hyperbolic disk and map it to the ideal star, and then develop by Schwartz reflection. So I want to be a little bit impressionistic here and just say a word about how you prove these theorems. So let me just say two words about it. So the first is, when you have the projective space over a number field, there's a natural way to measure the size of a point, the complexity of a point in this space. And what you do is you take some particular representation of that point in terms of coordinates, and then you take the product over all places of the field of the maximum over the coordinates of the v-adic absolute value of that particular coordinate. So it's a product of a bunch of things, and there's all these different valuations. Some of them are finite, some of them are Archimedean. It's a sort of complicated formula. It's beautiful that it doesn't depend on this choice of representative. That's because there's a product formula for all these places. But if you don't like number theory, or at least you only like the infinite places, that's like me, then you can get a good idea of what this height is. You just say you have to represent your point as a ratio, as a vector with integral coordinates. The coordinates should be integers in this field. And then you take a product just over the infinite places of the field, which everyone can understand. And that's another way of saying what the height is. And so to make a long story short, there's a comparable height that you can define for an abelian variety with complex multiplication, with real multiplication by the ring of integers. And it has to do with the Hodge norms of the projections of the integral cohomology classes on this abelian variety to each of the eigenspaces for the action of OK. So I don't, unfortunately, have time to do this in detail, but it leads to a proof that the things you hope are cusps are in fact cusps. OK. So the last thing I want to do is say a word about a more recent investigation. So I mentioned that every geodesic curve in moduli space has a cusp. That's somehow where these periodic trajectories come from. We can also show that every geodesic curve on a Hilbert modular surface, a two-dimensional guy, has a cusp. But what about Hilbert modular varieties? So if we wanted to study the Pentagon, we would have a curve on a Hilbert modular threefold. And we wonder if this automatically has to have a cusp. And the answer turns out to be no. The theorem is that I don't know what happens for the Pentagon, but I know how to make an example on a six-dimensional Hilbert modular variety of a geodesic curve which does not have a cusp. And it satisfies some additional technical condition to rule out the examples Martin was worried about. OK, so I don't want to go too much into the details of this proof, but I want to show you some idea of its setting. So the proof of this, the construction of this example uses triangle groups. So it's very hard in general to produce geodesic curves at all in any algebraic variety. So we know how to produce Teichmuller curves in moduli space. We know how to apply Heck operators to get more on Hilbert modular surfaces. But there's very few other constructions, except for one, which was invented by Cohen and Wolfart. There's a construction which takes as its point of departure a triangle group. So it turned out that if I wanted to build a counterexample like this, what I would have to do is find a triangle group which is not arithmetic, but is as anti-arithmetic as possible. So let me just say a couple words about it. So there's a general theorem that there's only finitely many arithmetic triangle groups. This can be greatly generalized. This is due to Takeuchi. There's a list of 76 such groups. But there's also a theorem due to Waterman and McLaughlin that there are only finitely many purely hyperbolic triangle groups. These are triangle groups such that all their Galois conjugates are hyperbolic. Here, all their Galois conjugates are spherical, except for the original group. And the theorem is that there's a single equidistribution theorem which contains both of these results. So I'd like to conclude with two quick glimpses into that theorem. So the first is part of the proof involves some complicated three-dimensional geometry. And I was finally able to get my head around this geometry by looking at the moving tablecloth game. So let me give you a game to play since we're about to go to lunch. So here's the moving tablecloth. It has, so those yellow stripes, those are really bad. But this green and this is supposed to be blue, but it looks purple, those are good. So here's what I want you to do, is I want you to roll a ball across this tablecloth with this moving pattern. Ball moves at uniform speed, and it can't ever go into the yellow. It can just barely touch it at an edge, but it's not allowed to go into it. So how would you move a ball across this pattern, these moving islands, so that it never goes into the lava sea of yellow? Does anybody have a solution? Yeah.
A diagonal.
Oh, a diagonal. Let's see what's next. Aha! Great. Yeah, that's a good solution. Does anybody have another solution?
Same slope, but starting at 1/3 of the edge.
Oh, yes, of course. You can do the same slope. There's many solutions that are translates of this. But what about one that doesn't go diagonally? You can stay stationary in the center, yes. No, that's actually a solution. That's important. But does anybody see another? Yeah.
Like when we hit the purple here, you go down into the green and then continue basically adding the independent diagonals.
I think what you're saying is correct, and let me show an illustration of it. This is probably what you're saying, which is you do something like this. I hope that's what you were saying. Okay, no. So this also works. So this, you sort of stay on a horizontal line, and then as you go up, you jump at just the right moments. Okay. Now, the thing that made this proof hard is there's a third solution, which looks like this. So that goes through the midpoint, but at just the right moment that it survives without having to go into the yellow. Yeah, so I should say what this is all for is the proof that that there's only finitely many what I call purely hyperbolic triangle groups, which are essential to the construction of the last exotic curve I mentioned, which is itself an exotic version of the curves associated to the regular pentagon. So, so we know that there's only finitely many triangle groups that have this good property, that all their Galois conjugates are also hyperbolic. And there's 11 that are known. I wondered if that's all there are. So let me just skip to the end. So that's an open problem I'll end with. Are there any more examples of purely hyperbolic triangle groups beyond the 11 I mentioned? It turns out a particular one of them, of type 14, 21, 42, plays a key role in my construction, but you see the numbers are pretty small. So last week I generated some experimental evidence about this. And the theorem is there's no other purely hyperbolic triangle groups with PQR less than 5,000. I seem to be stuck on the number 5,000. Now, let me say a word about this theorem. So there's, roughly speaking, 5,000 cubed values of PQ and R with PQ and R less than 1. So that's, I don't know, let's say a billion. Now, for each of those, you have to test all the Galois conjugates. The Galois conjugates are for an nth root of unity where n is the least common multiple of these three numbers. So that's also a billion. So there's roughly a billion times a billion tests that have to be done here. So I recently found out that many universities have enormous computing complexes, including mine. And I got access to 5,000 cores running parallel for half an hour and verified the theorem. And in fact, I modified the algorithm so yes, there's 10 to the 9 Galois conjugates that have to be tested, but usually it takes 2. And in extreme cases, it takes roughly 30. So So there was a way to test this theorem, which I'm pretty sure is true, with a total execution time of only 587 hours. So I just wanted to end with this because it was a new experience for me to find out about what enormous resources have been built to handle problems in genetics and protein folding and so on. And I think there's a lot of interesting experiments that mathematicians couldn't do before that can be performed now using these resources. Okay, so let me stop there.
Thank you. Are there questions? I'll give you the microphone because it's recorded, so whoever has questions, I'll come over.
Hello.
Hi.
Have you been able to think about, or do you know of, a connection between the congruence invariant and the J invariant for these billiards?
So I don't know what either of those are.
Your congruence invariant
Oh,
versus the J invariant, which is in modular form.
Ah, okay. So the J invariant is an invariant of, it's an invariant of elliptic curves, if I understand what you're saying, yeah? Yeah, okay. So let me back up a bit and say that the J invariant arises in the study of modular forms for SL2Z, this arithmetic group. That's of great importance. This thin group does not have a well-developed theory of automorphic forms. The group SL2O does, but the thin group does not. But that doesn't mean you should give up. Because, now where did Martin go? So Martin and his co-workers have developed, especially Martin and Zagier, have developed a theory of automorphic forms that's perfectly adapted to this setting and allows us to do some really remarkable things, especially in the case of genus 2. So the last time I was at Lumini, I drew some pictures, which took a whole semester at MPI to draw, but they were just to compute this one formula that Martin and Zagier had derived. So I think there's a lot of room for progress in that direction. Yeah.
So maybe a question about that that random walk picture you drew. It's like, how random would you guess it? Is it like Mobius function random or much more random, like from your?
Okay. So how random was that picture? So there was a number over here, k. So my belief is that as k tends to infinity, these variables become more and more independent. So that if I had drawn the very distant random walk, it would be converging to the standard random walk generated by a Bernoulli process, by coin flips. But as I say, I know nothing. I don't even know the average is 0. So there are a lot of interesting things to be investigated.
I was wondering myself about the finite index of the closure of the triangle group in the adelic. Can you hint towards a proof of that?
Yeah. So, of why it's yeah, sure. Okay. So this kind of theorem was proved by Serre in this old book on. Now I know there's an eraser here somewhere. Oh, okay. Oh my gosh. Okay. So there's. Yeah, let me just say a word about this. If you have an elliptic curve over Q, then people often study its torsion points of order L, where L is a prime, or the torsion points of order L to the n. This is isomorphic. Z mod L to the n squared. And the automorphism group here is SL2 of Z mod L to the n. And then there's an action of the Galois group of Q bar over Q on this, which gives a representation into this group. And so what Serre proves in his book is that if you could also put these all together and get a representation into SL2 of z hat, which would be the product over all primes of SL2 of the p-adic integers. And so what Serre proves is that this image always has finite index there, and the methods apply just as well. So the method is to first show that the group maps onto SL2 of z mod p for all p, and for almost all p. And there's the p's that are ramified in the field extension. In my case, they play a special role. I have to prove I get finite index there in the p-adic integers, but for most of the primes, one can use old theorems of Dixon to show that, I mean, I just had two explicit matrices, right? So if I had just taken these two matrices, then you would believe that this generates this group, because it generates SL2Z. Thank you, same 0. Okay, so that would generate this group. Now what we had up here was 2 plus epsilon n, but as long as this is a unit, it's just as good as being 1. And there's infinitely many, almost all primes it's a unit, and then one has to bootstrap to go from the sort of Henselian version to go from z mod p to zp. And then finally there's something called Gorsot's lemma, which is about how various simple groups can interact with one another. It says there's no interaction between the different primes, so surjectivity for each prime allows you to conclude finite index.
And that last part that you hinted at, that for the ramified guys, that's kind of by hand? You have
Yes, yes. So I learned how to use magma for that particular calculation. Yeah, that's by hand.
More questions? Seems not the case, so let's thank Kurt again.